Okay, I'll get started with today's class. Just wanted to begin with a quick announcement. You should have got an email about the course teacher evaluation. Once we get to 80% on the course teacher evaluation in the sections, then I'll credit everybody for the, I think it was a 1% evaluation bonus. So it's very helpful, those evaluations, and make sure you complete the evaluation. That was the only announcement. I'm going to say something about the final exam on Tuesday's class, and next week I'll get a practice final exam posted, but I'll leave that announcement to next week. Any questions on all that before I go on with the class? Is the final cumulative? Yeah, the final is cumulative. So it will cover the material that's on test 1, test 2, and since test 2. And it will weight the material through the semester evenly. If you're in my 211 class semester, it'd be the same arrangement. That covered all the material that we covered on test 1, test 2, and after test 2 in a evenly weighted on the final. Is the format similar to the previous exams? Yeah, the format will be similar to the previous exams. It's worth 150 points rather than 100 points, but it'll have the same proportions of multiple choice questions, same proportion of numerical answer questions, and fully worked out problems. I don't know exactly how many fully worked out problems, numerical answer questions, multiple choice questions there will be, but it'd be the same proportions. And again, if you took 211 last semester, you could take a look at that final. It'll be the same sort of arrangement, same sort of balance as that final. Okay, I'll get going with the content for today then. So in the last class, we talked about photons as particles of light, as particles of electromagnetic radiation. That was a modern physics, quantum physics idea. In today's class, we're going to talk about waves of matter, wave properties of matter, as another ingredient component of modern physics, of quantum physics. So today's class, I've got a list here. I'm going to introduce what we call the wave particle nature of matter, that matter has both wave and particle properties. I'm going to introduce it based on what was the wave particle nature of light, that light has wave properties and particle properties. And you can think of this, I think it's nice to think of it this way, as a kind of synthesis of matter and light. Our universe is made up of matter and light. And up until the beginning of the last century, we treated matter one way, we treated light another way. This is a synthesis of how we think about, treat matter and light. Matter and light both have wave and particle characteristics. Then I'm going to move on and show you some evidence for the wave nature of matter, because that's unexpected. And I'm going to draw that evidence from when we looked at the wave nature of light, which is now familiar. And the indication of the wave nature of matter, like the indication of the wave nature of light, was due to effects that are wave properties. They are what we call diffraction, they are what we call interference. So we'll talk about diffraction of matter waves, interference of matter waves. Finally, I'll talk about what we call the uncertainty principle. And this was sort of a landmark event in physics at the beginning of the last century, the introduction of the uncertainty principle. It was the end of a kind of mechanical, deterministic view of how the universe works. And it was the beginning of a fuzzy, indeterministic view of how the universe works. In the old mechanical way of looking at how the universe worked, in principle, everything could be known and tracked forever. In the new indeterministic way of how the universe works, there's inherently uncertainties. There's inherently things you can't know. So that was a huge change, a big change in how scientists viewed the working of the universe. Okay, so let's start with some general remarks, no formulas, equations here, about unification of matter and light, this big idea. So this is kind of the classical picture of matter and light on this slide. And then the next slide is the quantum picture of matter and light. And over here on the left, I've got the classical description of matter. And over here on the right, I got the classical description of light. And remember, our universe is matter and light. That's the world we live in, a world of matter and light. So in the case of matter, we think of matter as ultimately being localized, concentrated, discrete particles. And those localized, concentrated, discrete particles as carrying energy and carrying momentum. And we describe those localized, concentrated, discrete particles by their energy, by their momentum, by E and P. And so that's our picture. This is our picture of matter. What about waves? What about light? Light, we think of classically as a non-localized, kind of diffuse, smooth, continuous wave. And we describe it with the frequency of the wave and the wavelength of the wave. And if you want to tell you about this or that wave, I'll tell you about the frequency and the wavelength of that wave. I'll tell you the frequency F and the wavelength lambda. So that's our picture of waves. And here's a picture of an electromagnetic wave. You've got an electrical field. It's oscillating in time and space. The magnetic field component is oscillating in time and space. And they're characterized by the frequency and the wavelength of those oscillations. And so in this pre-1900 picture of the universe as matter and light, the classical nature of matter and the classical nature of light are completely different. Matter's particles and light is waves. What about modern physics, quantum physics? What's our quantum picture of matter? That's over here on the left. And a quantum picture of light. Well, in the quantum picture of matter, in the modern physics picture of matter, those localized, discrete particles of matter, they actually have kind of a fuzziness to them, a diffuseness to them. and they exhibit or they show wave-like properties. So they'll show interference properties and diffraction properties, and they show those interference diffraction properties with some characteristic frequency, some characteristic wavelength, the F and the lambda. That sort of parallels the peculiarities that we found for light. We found at the quantum level, the modern physics level, that light actually came in little packets. We called them photons, and that light was emitted in units of photons. So it was absorbed in units of photons, and it propagated in little packets we called photons. And those photons carried energy and momentum. They carried P and E. And so this is a more sophisticated picture of what matter and light are, a more unified picture of what matter and light are. So matter and light are no longer just particles in the case of matter or waves in the case of light. They're entities. They're things that exhibit both particle-like and wave-like properties. They're entities, things that have what we call particle-wave duality. So gone are the days of things being simply a particle or simply being a wave. In modern quantum physics, things are more complicated than simply being particles or waves. Those things, those entities are actually things that exhibit both wave and particle-like properties. Okay, so in that context, let me go back to Planck's constant. Remember that number? We introduced it in the last class. It's this tiny, tiny, tiny number here. 6.6 times 10 to the minus 34 joules seconds. And this number plays the key role, the essential role in this transition from classical physics to quantum physics, in that it sets the scale of this granularity of light, the photons of light, and it sets the scale of this fuzziness of matter, the wave-like properties of matter. So I think of that as, when we were giving out jobs to all the different constants of nature, the job that we gave to Planck's constant was to set the scale for light's granularity and matter's fuzziness. As an example, supposing, let me pretend I'm in charge around here. I mean, that would be kind of a joke, but let me pretend I'm in charge around here, and I'm going to set Planck's constant to be 0. If Planck's constant was 0, then the granularity of light would vanish, and light would just return to that sort of smooth, continuous, classical, pure wave light of Maxwell. And the fuzziness of matter would also vanish. Matter would return to that sort of classical, particle, discrete, like particles of Newton. So that would be if Planck's constant was 0. If Planck's constant were much bigger than it actually is. So Planck's constant is 6.6 times 10 to the minus 34 joules. It's a tiny, tiny number. That's why we only see these quantum effects at microscopic levels. If Planck's constant was more of an everyday number, let me make it 6.6 joules seconds rather than 6.6 times 10 to the minus 34 joules seconds. What would we see then? We would see in our everyday lives, everything would have wave-particle duality. Everything would have wave-particle properties. And so we would have been much more familiar with this notion of entities having both wave and particle-like properties. It would just be our everyday experience that entities have wave and particle-like properties, rather than it seems so strange, so bizarre, so peculiar that at quantum level, you know, that light has particle-like properties and matter has wave-like properties. So that's Planck's constant. So now let's turn to some equations. Let's try and quantify this world of matter waves. And I want to introduce this guy. So this is de Broglie. And de Broglie won the Nobel Prize. De Broglie won the Nobel Prize for the hypothesis that just like light has some wave and particle-like properties, that de Broglie's hypothesis that was particles also have wave and particle-like properties. And so it was kind of a synthesis of how we think about light and matter. They both have wave and particle-like properties. And it was a revelation. The fact that he got a Nobel Prize for that indicates that it was a completely revolutionary idea. It was a breakthrough idea that really was part of the birth of quantum modern physics that we know today. I actually love his name here. Look at this, Louis Victor Pierre Raymond, 7th Duke de Broglie. I mean, that is a great name. But normally we just say de Broglie. We say de Broglie waves when we talk about matter waves. So if you hung around the corners of the halls of the chemistry physics building, you might hear de Broglie waves here and there. And if you hear that term, de Broglie waves, that's matter waves. We're crediting de Broglie for matter waves. Okay, so I've added to this slide now where we've got the quantum description of matter on the left and the quantum description of on the right. I've added some equations. So over here on the right are the ones that we met in the last class. These pair of equations here are the relation between the wave-like properties of light, so frequency and wavelength, and the particle-like properties of the photons, so the energy and the momentum of the photons. And as you see, they're related through Planck's constant. And then over here on the left-hand side, this is the corresponding relations for matter waves. So in this case, I've got the familiar particle-like properties on the right, energy and momentum, E and P, and then I've got the wave-like properties of matter, the frequency and the wavelength sitting over here on the left. And again, it's Planck's constant that relates these two perspectives. And so this pair of equations here on the left is what de Broglie introduced. Remember, this pair of equations over here on the right, that's kind of what Einstein introduced. And again, this is really this sort of synthesis of matter and light into a common framework for imagining these entities, matter and light, where they both have wave and particle-like properties. Okay, so here's a good question, because I've been pretty radical and said that matter has wave-like properties. Well, think about those everyday objects, footballs, basketballs, and baseballs, and other everyday objects. They don't seem to exhibit wave-like properties. They don't seem to exhibit diffraction. They don't seem to exhibit interference. Why is that? Well, let me show you. This is an example of a calculation involving de Broglie waves or matter waves. So in this calculation, in this example, it says calculate the de Broglie wavelength of a 0.6 kilogram basketball with a speed 10 meters per second. So, you know, that is a mass of a basketball. And that is a, you know, sort of typical speed of a basketball. Maybe not if I'm throwing it, but that would be a typical speed of a basketball. And so what is the matter wavelength for that particular particle? What's the de Broglie wavelength for that particular basketball particle? So let's see if we can calculate that. There's two equations I'm going to use here. Firstly, I'm going to calculate the, this is sort of getting ready to calculate the matter wave, calculate the momentum of the basketball. And then I'm going to calculate the wavelength of the basketball. So those are the two steps, sort of A and B. So momentum. Well, momentum is mass times velocity. And the mass we were told is 0.6 kilograms. The speed velocity we're told was 10 meters per second. So that's 6 kilograms meters per second. We might want to rewrite it in these units here. Joules seconds over meters. They're equivalent units. So that's the momentum. Now we can go ahead and calculate the wavelength. So for de Broglie waves, the wavelength for a particle of momentum p is Planck's constant h divided by the particle's momentum p. So all we got to do now is take Planck's constant, 6.6 times 10 to the minus 34 joules seconds, divide it by the momentum, that's 6 joules seconds over meters. That's why I wrote it in those units, because then you can see clearly that the joules seconds in the numerator and the denominator cancel out. And we've just got going to get units of meters for our answer, which is the units of wavelength. And I've got numerically 6.6 times 10 to the minus 34 over 6. So that's actually just 1 point, I can do that in my head, 1.1 times 10 to the minus 34 meters. So, you know, basketball does have wave-like properties, but those properties are only exhibited at distance scales, size scales of the wavelength. You know, basketball interference, diffraction, would only be exhibited at distance scales of its wavelength. Its wavelength is 1.1 times 10 to the minus 34 meters. That's, I mean, that's tiny. That's smaller than the size of an atom, you know that. That's smaller than the size of a nucleus in an atom. That's smaller than the size of a proton or a neutron in a nucleus in an atom. So it's tiny, tiny, tiny. We're not going to see that. And so that's why we don't have to worry about the wave nature of basketballs when you're playing a basketball game. But what about, where do you have to worry about the wave nature of matter? Well, you do have to worry about the wave nature of matter for electrons in molecules or electrons in atoms. And so let's do the same calculation now of the matter wavelength or the de Broglie wavelength. But let's calculate it for not a basketball on a basketball court, but let's calculate it for an electron in an atom. For the basketball on the basketball court, I took the mass of a basketball and typical velocity of a basketball. For the electron in the atom, I'm taking the mass of an electron, and I'm taking the a typical speed of an electron in an atom. And that's about 1 million meters per second. And so we're going to calculate the de Broglie wavelength of this electron. Again, there's two bits here. Starting point is to calculate the momentum, because it's the momentum that is related to the wavelength through Planck's constant. And so I'm going to go again through parts A and B. So the momentum of the electron, its mass, 9.1 times 10 to the minus 31 kilograms, times its speed, 1,000,000 meters per second. And that comes out to be 9.1 times 10 to the minus 25 kilograms meters per second, or what's handier here, joules seconds over meters. So that's the momentum. Now we can just calculate the wavelength. So the wavelength is Planck's constant that sets the size scale of quantum effects divided by the momentum. Planck's constant, 6.6 times 10 to the minus 34 joules seconds. The momentum, 9.1 times 10 to the minus 25 joules seconds over meters. Again, look, I wrote it in those units, which might have seemed odd, but are handy here because you see the cancellation of joule seconds in the numerator and denominator. You're just left with the units of meters. And when you calculate the number, you get 7.3 times 10 to the minus 10 meters. Now that's still a small number, but it's not a small number compared to the size of an atom or a molecule. Atoms have that sort of size scale, nanometer size scales. Molecules have that sort of size scale. And so wave-like properties of electrons in atoms are important for the structure of atoms. Wave-like properties of basketballs on basketball courts were not important for the game of basketball. Okay. So that's introduced de Broglie waves, matter waves, and equations, formulas for de Broglie waves and matter waves. Let me talk about how matter waves were first observed, first seen. And in doing this, what am I doing here? In doing this, I'm going to talk about two famous scientists. One is Bragg and one is Davidson. They're from the last century. They both got Nobel Prizes. They actually got Nobel Prizes for experiments involving diffraction, which you might remember, we talked about diffraction earlier, and it's an effect associated with waves. One of them, Bragg, used diffraction to illuminate the structure of crystals. It was the first time, it was an amazing event, that we saw inside crystals, how crystals were laid out. So that was Bragg's Nobel Prize. And then Davidson used diffraction and crystals to actually show that electrons are matter waves. So he's the first person to actually see matter waves. So that was also a fantastic event. Okay, so here's Bragg. And as I say, the key thing about, I don't know if he went by William or he went by Bill, but the key thing that we'll call him Bill Bragg, he illuminated crystals. You know, like I remember, this takes me back to school. I guess it was middle school, maybe it was high school, growing copper sulfate crystals. I mean, I really enjoyed that. And you grow these copper sulfate crystals. If you could look inside those copper sulfate crystals, you would see this amazing arrangement of atoms and ions, this regular pattern of atoms and ions. And Bill Bragg was the first person to see that. And he did it with diffraction. And he got a Nobel Prize for that, so it was important. Okay. So in this slide, I'm trying to show you how X-ray diffraction of crystals works. So that's, I've titled it X-ray diffraction of crystals. So this is how Bill Bragg saw that crystals were regular arrays of atoms, ions. And he did it in a way that's very similar to something that we looked at with light and soap bubbles. That might seem weird to begin with, right? Why is, rainbows in soap bubbles, something from some weeks ago, similar to illuminating crystals with X-rays? Well, the reason they're very similar is that they involve a similar sort of interference of electromagnetic waves. So the visible light with the soap bubble rainbows, that was interference of visible light. And the X-rays on the crystals, that's the interference, again, of X-rays. They're also electromagnetic radiation. And actually, in both cases, you can really think of them as very similar. Soap bubble experiment and the X-ray diffraction experiment. It's very similar experiments, very similar phenomena. Remember when we thought about the soap bubbles, we thought about the reflection of the top surface and the bottom surface, the outside and inner surfaces of the soap bubble. When we think about diffraction, we're going to think about the kind of diffraction of the incident beam of X-rays off the top surface of atoms and then the next layer of atoms. And we'll see how the diffraction works. And so that's what I'm picturing here. So let me explain this. Downstairs here is a picture of a crystal. And you might imagine this is a sodium chloride crystal. So sodium chloride crystals are sodium and chlorine ions. There's smaller sodium ions, there's larger chlorine ions. And so in red here are the sodium ions, and in blue here are the chlorine ions. And they're kind of arranged in this lattice arrangement, regular arrangement. In from the top left comes some X-rays. Remember, X-rays are just short wavelength, high frequency electromagnetic radiation. They're friends of light. And over here on the right are outgoing X-rays. After being diffracted off the crystal here. And specifically, what I'm picturing is the diffraction from two consecutive layers of the crystal. So say the very top layer and the layer just below it. And so you see this upper beam here gets diffracted off the top layer, this lower beam here diffracted and off the bottom layer here. Now, that's the key, right? And that was the key to rainbows in soap bubbles. In rainbows in soap bubbles, the reflection off the top and the reflection of the bottom layer of the soap bubble, if there was a whole number of wavelengths between those reflected rays, then you got in constructive interference. That's how you made the rainbow. And the same is true here. If there's a whole number of wavelengths for this extra path, I'll show it here, that's taken by the diffraction of the bottom layer compared to the diffraction of the top layer, that's a whole number of wavelengths, you get constructive interference over on the right-hand side. So you get like that'll be like your X-ray rainbow. And so that's X-ray diffraction. And you can turn this picture here into an equation for when you get constructive interference. And that equation is called Bragg's law. And that equation for constructive interference is this little equation here. And all this equation is saying, over on the left-hand side, it's saying that the extra distance traveled by the X-rays diffracted off the lower plane compared to the upper plane. So this extra distance here, is this thickness here, that's D, times the sine of this angle here, that's this extra path here, times 2, that's the total extra path. So that's the extra distance traveled. If that's a whole number of wavelengths, if it's one wavelength, two wavelengths, three wavelengths, four wavelengths, and so on, then you get constructive interference. And so this is the Bragg law for Bragg diffraction. And this law enabled Bragg to see the structure of crystals. You see, it depends on the separation between the layers of the crystal. And so you can see in the diffraction pattern the different layers of the crystal. And so it was a fantastic experiment. Well, Clinton Davidson, he used that idea of diffraction of crystals. But instead of diffracting X-rays of crystals, what he did was actually diffract electrons of crystals. Now, before the days of quantum physics, before the days of modern physics, that would have sounded ridiculous. You know, the diffraction of the X-rays is a wave-like phenomenon and a feature of waves. To try and diffract electrons, if you just thought they were particles, would be close to lunacy. So he was trying to show that electrons do have wave-like properties by showing that electrons do exhibit diffraction, and they do exhibit diffraction of the lattice arrangement in a crystal. And so here I'm just going to try and quantify that. This is a picture now of electron diffraction from crystals, not X-ray diffraction from crystals. But you notice, other than changing the word X-ray into electron, basically use the same slide that Bill Bragg gave me for the X-ray diffraction. I've just made a copy of it and changed the words X-rays to electrons for electron diffraction. So now the way we picture electron diffraction of a crystal is, again, downstairs here. Imagine this is the sodium chloride crystal. Remember the sodium ions are the small red guys, and the chlorine ions are the big blue guys here. And they're arranged in these regular planes, this regular lattice. And here from the left comes this beam of not X-rays, this is electrons we're shining on the crystal. And those electrons are diffracted off the layers of the crystal through their wave-like properties. And so this upper diffraction is for X-rays diffracted off the top layer. This lower diffraction is X-rays diffracted off the lower layer. And if this extra path that the electrons are now traveling, if that corresponds to a whole number of electron wavelengths, then you're going to get constructive interference, and you're going to get, you know, a rainbow. This time, not of visible light, not of X-rays, but of electron intensity. And so you can again turn that picture into an equation. The equation is just determined by the separation between the two layers here, which determines the extra path that's traveled by the X-rays diffracted off the bottom layer compared to the top layer. That's 2d sine theta here. And if that's a whole number of wavelengths, 1 wavelength, 2 wavelength, 3 wavelength, 4 wavelengths of electron waves, then you get constructive interference. And so that's electron diffraction from crystals, and that's how electron waves were first directly observed. Okay, so as an example calculation related to electrons having waves and photon having wavelengths, let's compare, to get a sort of scale of things. Let's imagine that we've got in the lab here, or I've got in my office here, I've got a electron and a photon, and they both have energies 10 electron volts. Electron kinetic energy is 10 electron volts, and the photon's energy is 10 electron volts. Okay, I just got a question in chat. Let me read this. How did they see the diffracted electron be? Yeah, actually, that's a very good question. That's not a silly question at all. And you could ask it for the X-rays too. You know, how your eyes can't see the X-rays. How did they see the X-rays? You know, when we did it with the soap bubbles, our eyes could see the visible light, but our eyes can't see the X-rays in X-ray diffraction. Our eyes can't see the electrons in electron diffraction. One way you can see it is to expose a film, old-fashioned film, like in an old-fashioned camera, probably before you were born. But when I was born, we used to buy cameras where you used to stick film in it, and you would take pictures that way. And it sounds like, you know, like it was in the Stone Ages, but it wasn't in the Stone Ages. It was only decades ago. But anyway, you could put a film where the diffracted electrons are going, or the diffracted X-rays are going, and where you get constructive interference, you would get a dark patch on the film. Where you've got destructive interference, then you get no effect on the film. And so you can expose a film and see the diffraction patterns with X-rays or with electrons. And it's how the dentists used to do it in the olden days, right? They didn't have these computerized systems that record the X-rays of your teeth. They used to have films that recorded the X-rays of the teeth. And the films would also work with electrons if they did electron scattering off your teeth. Okay, but let's get back to the question. Let's get back to this question. We've got a photon in our dorm room, and we got a electron in our dorm room, and the photon has 10 electron volt energy, and the electron has 10 electron volt kinetic energy. And we're going to figure out the wavelengths, the corresponding wavelengths of the photon and the electron. And so I'm going to do this upstairs here for the electron and downstairs here for the photon. And again, it's 2 steps, right? Firstly, I'm going to answer the question, what is the momentum of the electron? What is the momentum of the photon? And then I can answer the question of what is the wavelength of the electron? What is the wavelength of the photon? So I'm going to go through those steps. The electron. So there's going to be an important point here. When I calculate the electron's momentum and I calculate the photon's momentum. When I calculate the electron's momentum, the electron of this energy is going much slower than the speed of light. It's non-relativistic electron. And so our use non-relativistic equations from physics 211 to calculate the electron's momentum. When I come to the photon's traveling at the speed of light, I'll have to use the relativistic equations relating momentum and energy from physics 213 to calculate its momentum. So with that, this is the relationship I'm using for the electron. I know it's kinetic energy, K. I'm going to calculate its momentum, P. And kinetic energy is equal to the square of momentum divided by twice the mass. Equivalently, half mv squared. But this is the relationship between kinetic energy and momentum. And I can turn that around. I did it here. The momentum is going to be the square root, twice the mass of the electron times the kinetic energy of the electron. So all I got to do is plug in the kinetic energy of the electron and the mass of the electron. Here's the mass of the electron. I'm using units of electron volts here. It's much easier to work in there. And I'm using here the kinetic energy in electron volts. That's how we were given it. And if I plug those numbers in, I get about 3,200 electron volts over C. That's the momentum of the electron. Okay, then I can plug in that momentum into this relationship between wavelength and momentum. This is the de Broglie wave relationship again. So we've used this before. And so I'm just going to take Planck's constant. I'm now using it in electron volts seconds. Divide it by the momentum here. Plug that in. Plug in all the values, right? And here's the wavelength. Here's the wavelength of the electron. And that comes out to be 0.4 nanometers. So that's the electron wavelength. Now I'm going to do the same thing with the photon. So with the photon, I've got to use the relativistic relationship that we met for photons and light between momentum and energy. So I can't use the non-relativistic relationship. Oh, so I was just seeing chat. That's actually a good question. Where did the 3 × 10⁸ meters per second come from? So that's a good point. I should have mentioned that. Energy is measured in electron volts. Mass is measured in electron volts over c squared, speed of light squared. So there's a c squared here. That's why I had a c here when I took the square root. So when I plug in to the de Broglie wave equation, Planck's constant and the momentum here is in units of electron volts over c. I've got to plug in that speed in c, 3 × 10⁸ meters per second. So that's the speed of light. That's going to give me the meters, which I need because I'm calculating a wavelength. And it will also give me an inverse seconds that'll cancel out this seconds here from Planck's constant. So I hope that helps with that. Otherwise, we wouldn't have had the units right in that equation. So it's actually a very good question, I think, because remember, we're calculating a wavelength. We've got to get units of meters. If we didn't carry that, if we didn't plug in the right units for the energy and the mass and carry that C with us and put in the value for that C, we wouldn't have got the right units. So it's good to mention that. Okay, let me go back to the photon. This is the relativistic relationship between the energy and momentum of the photon. All we got to do here, again, is divide the energy by C. And so 10 electron volts divided by C are 10 EV over C. This is a unit of momentum. Electron volts over C. Like electron volts over C squared were a unit of mass, like just electron volts are a unit of energy. So that's an important point too. Now again, we can go to the de Broglie relationship between momentum and wavelength, plug in Planck's constant, and plug in the momentum. Again, it's 10 electron volts over C. We're keeping that C. Then we're going to plug in the value of C, 3 times 10 to the 8 meters per second. And we're going to again note that the seconds in the speed of light will cancel with the seconds in Planck's constant here. The electron volts cancel out in the numerator and the denominator, and we're just left with the meters, which is the units of the wavelength. And now we get 100 Newton meters. Not Newton meters, oh my God. Sorry, nanometers, not Newton meters. So it's an interesting problem because we started with two objects, the electron and the photon. They both had 10 electron volts. But although they both have 10 electron volts, they're very different beasts if you think about them. So the electron is non-relativistic. It's moving much slower than the speed of light. The photon is relativistic. It's moving at the speed of light. And the wavelengths, their wavelengths, their corresponding wavelengths, although their energies, kinetic energy and total energy, their wavelengths are very different. Different by a scale of, you know, order of 1,000 different. Okay, last topic I want to talk about a principle that's called the uncertainty principle, or called, you'll see sometimes it's the Heisenberg uncertainty principle. And it's a principle related to the sort of indeterministicness of the universe, the sort of kind of fuzziness of the universe, the inability to predict things or to know things in the universe that came along with quantum physics, that came along with modern physics, that was not a part of classical physics, not a part of the sort of mechanical universe. At this point, I got a quiz question. Okay, I think time's up. So this is a question about matter waves, about the wavelength of matter waves. We're asked to think about the wavelength of the matter waves of a fast-moving heavy truck. Now look, a fast-moving heavy truck has a lot of momentum. It's a lot of momentum compared to, say, an electron in an atom. It's much heavier than the electron in the atom. It has much more momentum than the electron in an atom. The wavelength of matter waves is in inverse proportion to the momentum of the matter. So the more the momentum, the shorter the wavelength. So with everyday objects, we don't notice the wave-like properties of everyday objects because their momentum is so large, meaning their wavelengths are so tiny. So the wavelength of the truck is much, much smaller than we could ever measure, could ever see, could ever notice. Okay, so this last topic about the uncertainty principle, you may have heard of the uncertainty principle. It's sort of quite a famous thing in sort of general quantum physics. because it's a sort of general statement about how well you can and cannot know things, how well you can and cannot measure things, how accurately you can measure or can't measure things. And it's a feature of the quantum world that is absent in the sort of classical world. It's a indeterminacy, a fuzziness of the quantum world that is not in the classical mechanical world. And Heisenberg got a Nobel Prize for this. So let me just show you that you're actually familiar with the uncertainty principle for example, waterways. So the uncertainty principle is related to the fact that you cannot know simultaneously both the position of something, an object, an entity, and the wavelength of that sub-object, that entity. You can't know them with high accuracy simultaneously. And waterways are a nice example of that. So look, there's actually two pictures here. It didn't come out very clear, but there's a picture on the left and there's a picture on the right. And they're pictures of water waves. There's water waves here, you see the ripples on the left. And there's water wave here, you see this peaked wave here. And these two pictures show kind of extremes of the uncertainty principle applied to water waves. So in the picture on the left-hand side, if you look at that picture, you know the wavelength of the water waves pretty well. These ripples, right? Here's a crest of the water wave. Here's the next crest of the water wave. Here's the next crest of the water wave, and so on, right? You can see the wavelength. Maybe it's 10 centimeters. You can see it pretty well. So we know the wavelength there. But we can't say where the water wave is. We can't say the location of the water wave. It's everywhere in this picture. So on the left-hand side, we know the wavelength well for the water wave. We know we don't know the position well for the water wave. And remember, for matter waves, for photons, the wavelength is momentum are related. So we know the momentum well on the left-hand side, but we don't know the position well on the left-hand side. We only know one of those things. We don't know them both simultaneously. On the right-hand side is kind of the opposite situation. On the right-hand side, you see this is a really interesting phenomenon in waves. Not a very good picture of it, but it's actually called a soliton. You might want to Google that. But we know the position of this wave, right? It's this big peak here. So in this case, right-hand side, we know the position of the wave right here. I can tell you where it is. It's not down here on the bottom left. It's not up here on the bottom right. It's not up here on the top left. It's right here now. But we don't know the wavelength. This peak of water waves is actually made of lots of different wavelengths superimposed together. And I can't really tell you the wavelength. I can't see the wavelengths. So this is where I know the position of the water wave, but the wavelength of the water wave, which is related to the momentum, think of matter waves, is poorly determined. So this is a sort of water example of the uncertainty principle. And it was Heisenberg that applied this example to matter, to electrons, to atoms, to molecules, that you can't simultaneously know the wavelength of an electron or its momentum and also know its position. There's a limit on how precisely you can know these two things. The better you know the wavelength or momentum, that's the left-hand side here, the more poorly you would know the position of an electron. The better you know the position of the electron, the more poorly you know the wavelength or the momentum of the electron. So that's the basic idea. In quantum physics, in modern physics, you cannot simultaneously know the position and momentum of a particle, say of an electron. You know, in classical physics, there is no limit on how well you can know the position and momentum of a particle. You can know them simultaneously, very precisely, as good as you can measure them. In quantum physics, there is a theoretical limit on how well you can know the position and the momentum of a particle. You can't know them as well as you could, in principle, measure them individually. There's a limit on how well you can simultaneously know them. And so that's the uncertainty principle. Here's equations that describe the uncertainty principle. Let's start on this top one. This is the most familiar one, and then we'll go on to this bottom one. This is also a well-known uncertainty principle. So if you look at this equation, it looks sort of scary, I think, but it's not really too scary. Let's look at the ingredients. There's delta X here. Delta X is uncertainty in X, uncertainty in position. Is how well you can know the position. It's a limit on how well you can know the position. Delta P here. That delta is uncertainty, uncertainty of momentum, delta P. It's how well you can know the momentum. The product of delta X and delta P, what could that be? Well, the delta X is how well you can know the position. The delta P is how well you could know the momentum. The delta X, delta P is how well, the size of that determines how well you can simultaneously know position and momentum. And what this equation says, if you look at the right-hand side, is that there is a limit on how well you can simultaneously know position and momentum. And that limit is set by Planck's constant. Planck's constant divided by 4 pi. So the uncertainty in X and the uncertainty in the momentum always have to be bigger than Planck's constant over 4 pi. You can never know them better, simultaneously better than Planck's constant over 4 pi. And so that's the uncertainty principle. Now, you might know the momentum really, really well, and then you would only be able to know the position very, very poorly. Or you might know the position really, really well, and then you would only be able to know the momentum really, really, really poorly. And so that's examples of the position, momentum, uncertainty principle. And again, it's kind of reflecting matter's wave-like properties, matter's fuzziness. That you can't know everything about that water wave, and you can't know everything about this matter wave. There's limits on how well you can state its position and momentum. So there's a second famous uncertainty principle, and that's a relationship between position and time. Sorry, energy and time. That you cannot simultaneously measure a particle's energy and know the time that you've measured that energy at. So if you know the time really, really well that you measured the energy, you'll determine the energy poorly. If you know the energy really, really well, you know the time that you determine the energy at. poorly. So this is another uncertainty. And so in this uncertainty principle, delta E over here, this is how well you've determined the energy. It's the uncertainty in energy. It's the precision, accuracy, you know the energy. Delta T here is how well you know the time you measured the energy, the moment that you measured the energy. It's the precision that you know the time that the energy was measured at. The product of the two, right? That's how well you know this combination of the energy of the particle and the time that you measured the particle at. And the uncertainty principle says that that combination has to be larger than Planck's constant over 4 pi. So again, Planck's constant is setting the scale of this imprecision, this theoretical imprecision that you can know these two things at. So you could, for example, know the energy really, really, really accurately, but you wouldn't know the time that you determine that energy very well. Or you could measure at a given time very accurately, but you wouldn't know the energy. You wouldn't know the energy very well. The product would have to be greater than Planck's constant over 4 pi. And so those quantitatively are the uncertainty principle, Heisenberg's uncertainty principle. Here's just a little illustration of the uncertainty principle. So let's take a look at that. So in this question, we say we've got a 2 kilogram object, and it has an uncertainty, position uncertainty of 1/10 of a millimeter. And we're asked to figure out the minimum uncertainty in the object's speed. So this minimum theoretical uncertainty in the object's speed. So say this is a uncertainty principle question. We know how well we know the position of something, and so that sets a limit on how we can know the momentum of the something, in accordance with Heisenberg's uncertainty principle, that the product of the two uncertainties of the position and the momentum must be bigger or equal to the scale of Planck's constant over 4 pi. So if I want to calculate the uncertainty in the momentum or the velocity, that's what I'm going to do down here. I'm going to start with the fact that I know the uncertainty in the position, and I'm going to start with uncertainty principle. And so here's my starting point. The product of the uncertainties in the momentum and the position are going to be of order. This is the theoretical limit, Planck's constant over 4 pi. If I know the uncertainty in the position, delta x 1/10 of a millimeter, I can figure out the minimum uncertainty in the momentum. It's Planck's constant over 4 pi divided by that uncertainty in the position. I'm just rearranging the equation, uncertainty principle equation. And so I take Planck's constant, I divide it by 4 pi, I divide it by the 1/10 of a millimeter, and I get this is the momentum uncertainty. This is the limit on how well I can know the momentum. And then if I actually am asked how well can I know the speed or the velocity, well, let's just use the relationship between momentum and speed, or momentum and velocity. Let's turn it around, that the uncertainty in the speed will be the uncertainty in the momentum divided by the mass of the object. I know the uncertainty in the momentum. I know the mass of the object. I divide one by the other. Here's the uncertainty in the speed. So it's tiny, right? This was an everyday object with an everyday kind of position uncertainty. If you take an everyday object with an everyday position uncertainty and you calculate how well you could know, what is the theoretical limit on how well you could know its momentum or its velocity, you find that this sort of quantum limit, this modern physics limit, this Heisenberg limit on how well you could know the momentum or the velocity, is tiny, tiny, tiny. You could never measure it this accurately. So this theoretical limit is a theoretical limit, but you could never measure it that precisely for everyday objects. It's really, again, only at the level of atoms and molecules and subatomic particles that these quantum limits on how well you can know things and how precisely you can measure things are relevant. So that fuzziness, that uncertainty of nature, only becomes apparent when you get down to the level of the atoms and the molecules and the subatomic particles. That fuzziness, that indeterminateness of nature is not present in our everyday world. That's why we never noticed it. Okay, I'm going to skip that slide and just conclude. So, like the previous class, we introduced the idea that light has particle-like properties. In this class, we've introduced the reverse, that electrons, matter, have wave-like properties. And these are the two fundamental ingredients in modern quantum physics. And they are a unification, a synthesis of our understanding of matter and light. And like in the last class, we introduced some equations to describe the particle-like properties of light. In this class, we introduced some equations to describe the wave-like properties, the Broglie wavelength of matter. And so that was most of this class. And then finally, at the end, we discussed the uncertainty principle. This applies to light and photons and everything in the quantum world. That there is a natural indeterminacy, a natural uncertainty, a natural fuzziness to the quantum world, where you can't know things precisely like you can in the mechanical world.